This video is going to briefly show you how to graph using Verniers Graphical Analysis. So I opened this from my apps menu. We are going to use the sample data that is in this assignment here. So we're going to use this sample data to show how to graph using graphical analysis. So first thing that I'm going to have you do is you want to save your file. Remember, we talked about how important it is to save your file correctly. So I'm going to call this data set 1. And remember down here, we want to make sure that we save this as a Vernier graphical analysis file. That's going to allow you to be able to open it again later. I am going to replace it because I don't want that old one. And I'm going to start by formatting my data over here. So the first thing that we're going to do is go to column options. And our first column is going to be our spring constant. And the unit is a Newton per meter. And we are going to give a certain number of significant figures for this one. And it's going to be 2 significant figures. And we are going to show the error bars because we can. And it is a percentage, and it is plus or minus 10%, and that's according to the material that we're using. So I'm going to apply that. Notice it is labeled not only on my data column, but it is also labeled then down on my x-axis. I'm going to do the same thing with my y, and my y is going to be the period, and that's a unit of second. I am going to have it include my significant digits, I believe, and we have 3 significant digits. Nope, we didn't do, we did decimal places. We're going to do 2 decimal places. I remember that now. And our fixed value, I believe, is going to be our 0.05 seconds was what we used as an example in lab today. All right, and so you're going to go ahead and enter your data. All right. Okay, so now we have our data set done. We're going to do a few things, or data entered. You'll see the error bars. We're going to now edit some of our graph options. So you'll come down here to the graph options button. And first thing we're going to do is scroll down to edit graph options. We're going to title our graph, which is the period versus spring constant. And we want to scale from 0. And we'll talk a little bit more about why that is in class, but we're going to show from 0. And we do that for a couple of reasons, but primarily it's because asymptotes and intercepts are important in physics because they always have meaning. And so we want to make sure that we can see those, and we need to be able to see the axes in order to see either an intercept or an asymptote. So we have our data, and one of the first things that we're going to want to look at is putting a fit. Now that we have our data well represented, we want to put a fit in. And to put a fit in, we come down here to our graph options, and you'll apply a curve fit, and there's multiple options that you can choose from. So we're going to start with a linear fit because it's the simplest, and why make things harder than they have to be. When you're fitting data, you want to always think of 2 questions. And the 2 questions you want to fit a curve to your data. You want to ask, number 1, does it fit? And then the second question, does it make physical sense? So if we look at the fit, we look at how close the line is to our data points. Does our line, our curve, fit within the error bars that are on each of our data points? We also look here at this number, the root mean square error. That tells you how far the data point is from the line, and we want the smallest number as close to 0 as possible. And it's an okay fit, but it's not a fabulous fit, is what I would say in terms of does it fit? The next thing we want to look at is, does it make physical sense? When you look at does it make physical sense, you want to ask yourself, are there intercepts, asymptotes that you need to consider? or that are present on the graph that will help you figure out if this makes sense or not. So, for example, we have an intercept right here. That y-intercept is about 1.5 seconds. So what that intercept would physically mean is if you have a spring constant that has a 0 spring constant, that would mean we'd have a y-intercept of 1.5 seconds. That makes no sense whatsoever. If we continue to decrease our spring constant, meaning essentially that would become a looser and looser and looser spring, right? So it essentially like approach a wire, right? And what that's going to do is that's going to create a period that is going to approach infinity, right? So we're going to have an asymptote there on that axis right here. And so the linear fit does not pass either one of those two tests. Does it fit is one of the tests, and does it make physical sense? We would also, if we were to zoom out, we'd have an x-intercept over here, which would mean that at some spring constant, we would end up having a negative period of time. And that also does not make any sense. So the linear fit, bye, it's gone. So the next couple of fits that we could look at, the next one on our list is a quadratic. That's a parabola. Again, that's going to have intercepts. It's not going to asymptote. That's not going to make a whole lot of sense. So let's try power, right? Let's try power function. And let's apply that. When we look at the power function, our curve goes through almost all of the error bars for each of the data points. So that hits our, does the curve fit the data? Our root mean square error is also smaller than it was with the line. So both of those are good. So that first question of does the curve fit the data, that's a yes to both of those, right? And then we ask, does it make physical sense? Is this function, this equation, is it representing what we think we are going to see? And if we were to take a little bit of time and zoom out of this graph, so I'm going to just make this really big. I'm going to make this one really big. You're going to see asymptotes on either of those two axes, right? You've got an asymptote over here and another asymptote over here. That's going to make physical sense because as we increase that spring constant, that period is going to get smaller and smaller and smaller, right? As that spring gets stiffer and stiffer, that spring constant is going to get, that period is going to get smaller and smaller and smaller. And it's going to approach zero, right? Again, as we decrease our spring constant, what happens to our period is just going to get longer and longer and longer. And that makes some good physical sense to us. I'm going to go back and look at our kind of original view. So that we can see what that looks like. So our power function is going to make some physical sense to us. And in the next video, I'll show you how to write the equation using the power function. But when you look at a function, you also want to look for patterns, trends, or things that are familiar. So this number is the exponent or the power, and it is a negative 0.4821. And while that looks kind of random and like it doesn't have a lot of meaning, it actually has a whole heap of meaning. The first is that negative, remember a negative exponent is going to mean that that variable is going to be in the denominator. The second thing that's important about that is the value of that exponent is about 0.48, which is really close to 0.5, and 0.5 in a power right there, that means square root. So we've just learned two things, that the period is now going to be inversely proportional, right? Because that negative means inverse or on the bottom. And then the square root is represented by that 0.5, 0.48. That is going to be what power we take our spring constant to. So we